Okay, and we are now recording. So the first question I wanted to go through today is a Gauss's law question, and it actually follows a problem that we were working on in yesterday's PAL session, where I gave you some different charged objects. I wanted you to tell me what Gaussian shape or Gaussian surface would you use to calculate the electric field of this object. And I also asked you to find the enclosed charge that you would use if you were going to do the calculation. So the last question that we went through in that last PAL session was what I'm showing you here. So this system consists of a charged rod or a charged wire, and that's the green one. Oh, and I didn't tell you which is positive and negative. I'll do that when I write it out in a minute. So we have a charged wire. It's like the green cylinder in the diagram here. And then there's a charged shell, and it's a cylindrical shell that's around the wire. And so what we're going to do is go through an entire Gauss's law question to find the electric field outside of this system. So in yesterday's PAL session, for those of you who were there who have watched the recording, we got as far as saying that in order to use the symmetry of the system, to our advantage, use it as much as we can, we decided to use a cylindrical Gaussian surface. So this blue cylinder, I don't know why the front of it is white, it just copied and pasted weird, but the blue cylinder in my diagram here, that will be our Gaussian surface. I've drawn it so that it has a radius bigger than either the shell or the wire, because we want to calculate the electric field outside of both the shell and the wire. So my Gaussian surface is outside of both of those. Now, I just realized I forgot my phone in the other room, so I have no way of checking the chat for questions as I'm talking. So, okay, here's what we'll do. I've said just kind of in this question here that the wire has a linear density lambda, and I guess I can kind of write this as we go. So it has a lambda, and it's going to be negatively charged. So lambda is some negative charge density, linear charge density. And this charged shell has a density sigma, not to be confused with a 6. I know they look similar. And sigma is going to be a positive charge density. So the negative wire surrounded by this positive shell. And what I want you to try to do, and this is where our last PAL session kind of ended off, what I want you to try to do is come up with an equation that would explain or calculate the amount of charge enclosed by the blue Gaussian surface. And I'll give you the variables that I want you to use. So the radius of our Gaussian cylinder, I guess, we'll call this lowercase r. And it's going to have, that is a rough arrow. I'll draw it better in a minute. But your Gaussian surface, the cylinder, is going to have a length of capital L. So what I want you to do while I go grab my phone so I can check the chat is I want you to try to come up with an expression for the total charge enclosed in your Gaussian surface using these variables. I'll be back in a minute. Yes, thank you. Okay, once you've come up with an expression, if you find something, if you're stuck, that's okay. But if you have a guess or have found something, can you put your answer in the chat? And that'll give me an idea of if you've had enough time to think about this at least. And so for those of you who are new to my PAL sessions, and I think I saw a couple people who haven't been here before, so welcome. I'm going to do this thing. I'm going to put a message in the chat that says ready to continue. So if you have an expression or like a way to calculate the amount of charge enclosed in your Gaussian surface, like please send that in the chat. If you're not really sure and you'd rather just see me do it, or you've tried but you don't think it works and you just want to see what the answer actually is, give my like ready to continue message, give it a thumbs up reaction or something like that, just so I know that you're ready to move on. Then I'm not sitting here waiting awkwardly while you're sitting there waiting awkwardly for me to go, and I'm not rushing you that way as well. Okay, looks like we're pretty much ready to move on. So to calculate the total amount of charge in the that's like contained in our Gaussian surface, let's do it for one object at a time. And so once we found how much charge from the wire is contained in the Gaussian surface and how much charge from the shell is contained in the Gaussian surface, then we can just add those together. So for the wire, I'll try to write that legibly. Okay, so the wire has a charge density lambda, which is equal to a charge per length. This is a lowercase l, that squiggly line. And so this amount of charge per length, that's constant. So what we can say is that lambda is specifically equal to the enclosed charge. I'm going to put a subscript W here, just meaning the enclosed charge of the wire. And so we'll have enclosed charge of the wire, and this will be divided by the length that it's enclosing. And that is just this length, and I'll draw it out properly here. This length of the Gaussian surface. And so that's the length that we would use because that's the length that is kind of limiting where or like what charge we're looking at in the wire. So the charge enclosed from the wire is divided by L. That's the length of our Gaussian surface. And so we can just, I guess that's lambda there. So we can say the charge enclosed from the wire is equal to lambda times the length of our Gaussian surface. And I see that in the chat, so nicely done. Okay, and so now we can do the same type of thing, but for the cylindrical shell. So we'll just call this the shell. So the shell has a charge density. It's an areal charge density. So that means sigma is a measure of charge per area. Looking specifically at our Gaussian surface, this will be a charge enclosed by the Gaussian surface, subscript S for shell, just to differentiate the two. And that will get divided by the area of the Gaussian surface. That one's not quite as easy to just read off, so we'll have to do a little bit of work to figure out which area that is exactly. So the electric field lines, we'll do them in blue because we don't have too much blue here yet. So the electric field lines from this shell are kind of coming out of the shell. I mean, technically, they would also be coming like out of the screen towards you and into the screen from the other side. But we've got all these electric field lines coming out. And so the area of the Gaussian surface that they're like coming in contact with is the area or the part of the Gaussian cylinder, that imaginary cylinder we've created. It's the area that goes around the shell. So we're not going to include these areas on the end here because there's no electric field going through that. So it'll be the area that's actually going around the shell. I'm going to add this second kind of measurement of our cylinder here, and this is the little r. And okay, so that looks like a V. All right. So the area of the Gaussian surface that we're considering, that's going to be the circumference of the around the cylinder multiplied by the length of the cylinder. That'll give the area that we're looking for. So we'll have the circumference 2 pi r, and that'll get multiplied by L, by the length of the cylinder, to give the total area. So coming back to this idea of the shell here and figuring out the enclosed charge from the shell, we'll have the enclosed charge divided by 2 pi RL, and so the charge enclosed and the charge on the shell that's enclosed, I should say it that way, going to be equal to 2 pi RL. This should be sigma. I wrote a lambda there by accident, but no, that should definitely be sigma. So we can just kind of combine these together and add them and say that the total charge enclosed is equal to lambda L plus 2 pi R lambda L, sorry, not lambda, L sigma. Okay. And so there is the total charge enclosed by our cylindrical shell. Okay, I want to pause here and see if there's any questions. And so, again, for those of you who are new, if you have a question, write it in the chat. If you don't have a question, I still want you to write something in the chat so I know that you're not still typing. So you can just write like good or, you know, all good, move on, stop wasting your time. I don't know, whatever. Make it something nice, please. But yeah, just let me know that you are ready to keep going. And so once I see a message from everyone, we can continue on and actually use Gauss's law to find the electric field. Oh, okay. Question in the chat says, would the lowercase r be the medium cylinder, not the Gaussian one? Okay, good question. So what you're saying is, I'll write it on this side, should this radius here be lowercase r, the radius of that shell? And actually, it's not. And the reason is because we're looking at, well, okay, back up a bit. We want to calculate the electric field at any point or any distance, I guess, from the shell. So any point outside of the shell, which means we need a variable that can be any distance outside of the shell. So if you make your lowercase r, if you say that's only the radius of the shell itself and it can't be any bigger than that, then you're saying that your Gaussian surface is right on that cylinder. And what you're doing in that case would be to calculate the electric field right at the surface of the cylindrical shell. That's not what we're trying to do, though. We're trying to calculate the electric field at any distance outside of the cylindrical shell. So that's why I made R. It's a bit of an arbitrary measurement, I guess, because it's the radius of the Gaussian cylinder, which, again, like, it's not a real object. It's just the tool that, I don't know, the imaginary shape that we're using. And so that lowercase r representing the radius of the Gaussian surface, the Gaussian surface can be any size. So that lowercase r can be any length as long as it's outside of the cylindrical shell. And in that case, it can be as far away from that shell as you want. And so depending on the value of r, we'll be able to calculate the electric field at any distance outside of the cylindrical shell. Does that answer your question? Or is there something else about it I haven't quite hit on yet? Yes, good. Okay, moving on. So, so we have our charge enclosed. Well, okay, let's actually write out Gauss's law to see how exactly we're going to use this. So Gauss's law says the flux, so that's the integral over a closed surface, a closed area, so that's our Gaussian surface, of the electric field dotted with the area is equal to the enclosed charge divided by epsilon naught. And so we have our enclosed charge up here. It's a bit of a gross formula, but we have it. Epsilon naught is a constant, so we've got that too. That's great. Next, what we need to do is tackle this left-hand side of the equation here, and actually isolate the electric field. So there's a couple things we need to address. For one, we need to check that the electric field goes straight through the surface, at our Gaussian surface, straight at a 90-degree angle. And the reason I say that is because we have this electric field dotted with a part of the area, and that's equal to, just using the definition of a dot product for a minute, and we'll forget about the integral for a minute too, that's equal to the magnitude of E times the magnitude of dA. I'm putting that in brackets just to remind you that it's just one variable, times cosine of the angle between those. And I just realized I was talking about an angle of 90 degrees, which is going to be super confusing. So give me a second to clarify that. This awkward looking shape here is going to be a little piece of an area. And this white line coming through it, that's going to represent an electric field line. And this is a little piece of the area of the Gaussian surface, this green weird shape. The area is, well, it's hard to describe an area with just one vector, because you could say, well, a vector that points in this direction is like kind of parallel to the area, or a vector that points in this direction is also kind of like on that area. And so what we use instead is just one vector that's parallel to the area. And by parallel, I mean perpendicular. Oh my goodness. Okay. So what I mean is that we use a normal vector, something that's perpendicular to the area. So for example, if you have the surface of a book, the front of a book, the vector you would use to describe it would come straight out of the book at a 90-degree angle from that flat surface. So the dA vector is actually at 90 degrees to the surface itself. What we need to double check and make sure is that the electric field is also at a 90-degree angle to the surface, so coming straight through the surface, not at some slanted angle or anything, so that the vector dA and the vector E are parallel. And if they're parallel, then this theta, that's the angle between the vector E and the vector dA, this theta will be 0. And so we can get rid of the dot product altogether and say that we can just write this integral then as the integral of E dA. No vectors, no dot products, no anything annoying like that. So we just need to double check that that is the case. Going back up to our diagram here, I've overshot it a little bit. We're saying that the electric field lines are going to come out of the cylinder and the cylindrical shell in all directions. And the Gaussian surface is going kind of around the cylindrical shell. And so when the electric field lines come out, you can see an example here. The electric field line intersects the Gaussian surface at a 90-degree angle. And that'll be the case at any distance for any electric field line. Looking at it from the side, or I guess more like head on, if you have, here's the wire with the shell around and your Gaussian surface around that. Ooh, that is a rough Gaussian surface. We'll try that again. Okay, your electric field lines are going to come in or out, not really sure yet, but that's okay, in or out of the wire and wire and cylindrical shell. And they're going to be at 90-degree angles to your Gaussian surface the whole way through. So that's good. The Gaussian surface is always going to have the electric field lines going straight through it at like a 90-degree angle to the surface. So we can absolutely cancel out the dot product because the angle between the area vector, the dA vector, and the electric field, that angle is 0. Okay, so we don't have any vectors on the left-hand side now anymore. So that's cool, that's nice. The next thing that we have to check is if the electric field is constant on the area of the Gaussian surface. Because if it is constant, for those of you who have learned integrals, that means we can just treat it as a constant multiple and bring it outside of the integral. So it won't actually be a function of the area or anything. For those of you who haven't done integrals yet, you'll get there, and this will make sense eventually, I promise. And in the meantime, you'll just have to take my word and Amy's word and the textbooks. Just take it as it is. So let's check and see if the electric field is constant on this surface. And well, we kind of set it up in a way so that it would be, because as the electric field lines are coming out, they're going to be like the electric field lines. They'll cross the Gaussian surface at the same distance from the like from the center of the wire and from the shell. They'll always cross the electric field lines at the same distance. And so the electric field line, or the electric field strength rather, will be the same, or will be constant in this area of the Gaussian surface. So that all checks out, which means that we can write this electric field outside of the integral. And so we're now just left with this E times the integral dA is equal to Q enclosed over epsilon naught. Okay. Now we have this integral dA, and there's nothing inside the integral. There's no function in there, there's no anything. And so what that means is that, and I'll write it off to the side here, the integral times the dA is just equal to the total area of the Gaussian surface. So we can write that this is just the electric field times the area of the Gaussian surface is equal to the enclosed charge over epsilon naught. Okay, so we've gotten rid of the dot product and the vectors. We've gotten rid of the integral now as well. So all the scary stuff's gone. We just have some algebra to wrap up this question. So the area of the Gaussian surface, we actually calculated that before. That was 2 pi r times L, so r being the radius of the Gaussian cylinder and L being its length. And that's equal to the enclosed charge. We also calculated that before, and someone was so smart and so kind as to put it in the chat. And so that enclosed charge is lambda L plus 2 pi RL sigma, all divided, well, and then we have divided by epsilon naught. That's not part of the enclosed charge, that's just the formula. Okay, and so now finding the magnitude of the electric field, really all we have to do is just divide both sides by this 2 pi RL to isolate the electric field. Okay, so I guess the L's all go away. That's kind of nice. And so write this as lambda plus 2 pi r sigma divided by 2 pi r epsilon naught. So I did divide both sides by 2 pi r and just canceled out all of the L's. And I guess depending on how you like to see your answer, you can simplify this. I don't know if it's simplifying, but you can write it as 2 fractions if you like the look of that better. I kind of do, because then the pi's cancel out in the second one. And so in any case, that ends up being the electric field strength outside of outside of both the wire and the cylinder. Okay. I'm going to zoom out a bit so you can see the last several steps. Does anyone have questions about any of this? And so if you have a question, write it in the chat. If you don't have a question, write good, all good, get a move on, something like that. I see a couple people have just joined us within the last couple minutes. You'll be able to see the earlier parts of this question in the recording. I'll make sure to give both of you access to that. and I'll put and you'll be able to see the link, like the link to the recording will send in the chat automatically, so you can click it there and I'll give you access. Okay, so in the chat, someone's asking, there's two R's, aren't there? The radius of the sleeve and the radius of the Gaussian surface. Actually, in our calculations, we stuck to just one letter R. That lowercase r only represents the radius of the Gaussian surface. And because we're saying that we're calculating the electric field outside and only outside of the cylindrical surface, we don't really need to define its radius. Does that clear that up? Oh, okay. So they're asking, don't you need the radius of the sleeve to find the area and come up with the charge from the sleeve? No, actually, you don't. And here, I'll explain why. So, okay, this this equation here, where I have just a random Q divided by a random A, you could look at that and say that it's a charge, some amount of charge on, so I don't know, maybe on this segment of your of the surface. It has a certain charge Q. I did not leave myself enough space to write, and an area A. Looking at any piece of the area of this cylindrical shell. What we said specifically, though, was that the charge density, the charge density, we said it would be the charge enclosed by the Gaussian surface divided by the area of the surface. So that's what we said before, was that it would be the area of like the Gaussian surface. What you're saying though, and I think you might be right. Okay, let's go through this. What you're saying is it should actually just be an area on the surface, on the like the cylindrical shell itself. Yes, yes, you're right. Thank you for catching that. Okay, so everyone here and everyone who watches this after, thank you for catching that. Yes. Okay, so we do. So there are two R's, yes. And to avoid confusion, I'm going to call this one uppercase R and fix that through my calculations. And I guess those of you who have just joined, you get a bit of a crash course of what we just did. Okay, so the radius of the shell, we're calling that capital R. And so what we're saying is that this sigma is some charge on the cylindrical shell, and it should be divided by some area on the cylindrical shell. And so the area of the shell will include the radius of the shell with the length of the Gaussian surface, because it's that length of the Gaussian surface is like that's how much charge we're considering. So, and I'm gonna keep my corrections in this lavender color, so you can pick out what's different. So this area then, the area of the Gaussian surface is 2 pi little RL. That's the area of the Gaussian surface itself. The area on the, the area on the charged shell that's surrounded by the Gaussian surface, that's 2 pi capital R L, lowercase l. I guess that part's the same. Or no, the length of the Gaussian surface. There's only one L. Okay. So yes, as you said in the chat, and thank you so much for catching that, it should be just the radius of the cylindrical shell here, because we're looking at this is an area on the shell, and we're looking specifically at a length L because that's how much is included in our Gaussian surface. So I hope I'm undoing some of the confusion that I caused earlier. Let's go through our solution and fix that for the rest of the problem. So this charge enclosed should include the radius, the capital R radius of the shell. That'll be capital R there as well. Then we went through and we checked some things about the integral to make sure those were all good. And okay, so when we went to plug in this enclosed charge, this should be a capital R, this should be a capital R, and we'll get rid of me trying to make it simpler because that's just not going to happen. This should be the radius of the cylinder, like the cylindrical shell, and as should this. Okay, thank you so much for catching that. Keep an eye out. Keep an eye out for what I'm doing. Sometimes it's inattention errors. Sometimes it's mixing up my variables like that. Okay, are there any other questions?
So how many conduction elements are there in the one memory? How can you find that out?
Yes, you are absolutely thinking of it right. I was the one that was mixed up for this question. Okay. Okay, so there is our Gauss's law question. I do want to point out, Amy's probably told you this, but as well, but she said that you won't have to actually do a Gauss's law, like a full Gauss's law question on the test, because that would just take way too long. So you won't have to do all of these steps, all of this. I just thought we would do one full example so that no matter what part of a Gauss's law question you end up having on your test, you'll have an example of what to do. Okay, so there's our Gauss's law. If you have any questions about it later on, please do put it in the chat. In the meantime, I think we'll go and do a textbook question that someone sent me. And it's about electric flux given an electric field, and we have a box for this question. Okay, there we go. Okay, so for this question 15, we have a box, and actually I'll draw the box because I find it's always easier to visualize things. That helps with these types of questions. Okay, so here's our three-dimensional graph. Okay, and the axes, here is our positive x-axis, here's the positive y-axis, and here is the z-axis. And there's a box sitting in this coordinate system, and I'll even draw it nicely for you. So this, So this box is sitting, it says sitting at the origin, and its edges are lined up with the X, Y, and Z, the X, Y, and Z axes. So I have attempted to draw that here, and I think it's good enough. And so, okay, and I guess the last thing is that each of its lengths are 1. So this would be at Z equals 1. This intersection here would be at Y equals 1, and this is at X equals 1. And so we have an electric field then, which has components of (350x) plus 150 I hat newtons per coulomb. Okay, so first off, this electric field only has an I hat component. It's not a uniform electric field. It's not constant because it depends on the X, and that's going to cause some headaches. But I guess the big takeaway is that it only has an X component. So the electric field lines are then only pointing, the way I've drawn it here, only pointing to the right. Sorry about that. Okay, so here's some electric field lines. I won't add too many, but they're all in the X direction. Okay, so if they're in the X direction, there's actually only 2 surfaces of our cube that are going to have any flux through them at all. Because these lines, I guess I can drag this one around to show you. This line is just going to sit on this top surface or be underneath of it and kind of go through the cube under the top surface, and same for the bottom. None of these like horizontal field lines are actually going to go through the top surface of the cube. Same thing with the front and back surface. So the field line can go like behind or in front of the front and back surfaces, the ones in the ZX plane, if it helps to think about it that way. But no field lines will actually like intersect that surface. So there's really only 2 sides of the cube. It might get messy if I try to draw them in, but it's like this square here. Oops. And this square here. Those are the only 2 sides that the electric field lines are actually going to go through. So there's only flux through those 2 sides. Okay, so let's look at the flux for this first side. And this first side is the one that's like lined up with the origin. And so I just want to point out that the x value for this first side is equal to 0. So the first side for where x equals 0. The flux through this first side, and I'll just call it flux 1, is equal to the electric field here dotted with this area. I'm just giving them all subscripts 1 for the first side. Okay, the electric field lines are going to cut straight through these two surfaces. So the electric field lines and the area vector, they're going to have a dot product. Well, I guess there's no angle between them, is the main idea. Like we were talking about before with our Gaussian surface. So the dot product will just end up being the magnitude of the two electric fields. Not electric fields, it's two vectors. One of them is an electric field, the other one's an area. Okay. So let's calculate what exactly the electric field is at, or the magnitude of the electric field. So we're dropping the I hat, doesn't need to be a vector anymore. And we'll calculate what it is for this surface. So the electric field is equal to 350 times x, but x is equal to 0 for this surface. So we'll have 350, I mean, it'll end up just being 0, plus 150 Newton per Coulomb. And that'll have units Newton per Coulomb. And then it'll get multiplied by 1 centimeter square. And we might as well just keep it in centimeters squared here, and just have our final answer in units of centimeters squared. This will get multiplied by 1 centimeter squared. If you had to do more complicated calculations with this, something I don't know. If you had to do something with more context, you should probably change the centimeters to meters. But for the sake of just defining the flux, we can totally write it in terms of centimeters squared. So we'll end up then with 150 Newton centimeters squared per Coulomb is the flux through that first side. Wouldn't it be centimeters cubed? Question in the chat. No, actually, because we're only looking at the area. This area that I squiggly shaded in green, I'll do it again in blue so you can see exactly which one I'm talking about. This area here is what we're looking at, and we're only multiplying the electric field by this area. So it should just be 1 centimeter by 1 centimeter to get just that one side, and so that'll end up being centimeters cubed. Yeah. Okay, perfect. Are there here? We'll do the second side, and then I'll check if there's any questions, and then that'll probably wrap it up for today. So that was the flux through the first side. Now we'll do the flux through the second side. Just write it down here. Can someone let me know in the chat what should be the value of x for this second side? Perfect. Yeah, x is equal to 1 centimeter. Absolutely. Okay. So for the second side, we'll have the same type of process. So the flux through side number 2 is going to be the electric field at the second value of x dotted with the second area. The dot product is just going to be the magnitudes of the two vectors again, because they'll be in the same directions before. What does the symbol between the 350 and 150 stand for?
Okay, so now, I see. So now instead.
Okay, in the original question here, it's 350x, plus 150. So that x is just like the x value on the of the coordinate system. Is that what you meant? Or I might have written something weird too.
Okay, so yeah. Okay, so we do have
Oh, that, huh? Yes. Good question. Okay. Yeah, I do my zeros with smiley faces in them. I had a high school teacher drill that into me for who knows why, but he did, and it's a habit I haven't been able to break. So yeah, that would be a 0. Yeah, thanks. Thanks for bringing that up. Okay. So, so now we have the electric field at the second value of x, which is getting multiplied by the area of that second side. It's a cube. All the areas are going to be the same. So the area will still be 1 centimeter squared. The electric field here, though, will be 350 multiplied by 1 plus 150 newtons per coulomb multiplied by 1 centimeter squared. And I just realized I'm using dots for dot products as well as for normal multiplication with numbers. And I'm sorry about that. That probably is confusing. I just find it's tidier than putting a whole bunch of brackets in. And since there's no vectors on any of these, and they're numbers, that context tells you that it's not a dot product. Okay, yes, because otherwise the 0 would look like an O. I'm with you there. Okay, question in the chat. The electric field would increase linearly as x increases. Yes, absolutely. Yeah, the electric field does depend on x for sure. Okay, so this flux through the second surface then is 500 Newton centimeters squared per coulomb, I believe, assuming I did my math right, which who knows, maybe I didn't. But yeah, that's the flux through the second side. And so the net flux then is going to be the difference between these. And a way you can think about it, is it's like 150 Newton centimeters squared per coulomb. That's the flux going into the box, but 500 Newton centimeters squared per coulomb comes out of the box. And so overall, there's like a difference in flux of 350 Newton centimeters squared per coulombs. Out minus n. Yes, exactly. So we'll write that out here. I do see there's another question in the chat. I'll get to that in a second. I just want to write this out before I mess it up. So the net flux is going to be equal to flux 2 minus flux 1, or like someone said in the chat, the outgoing flux minus the incoming flux. And that'll be 500 Newton centimeters squared per coulombs minus, 150. So overall, there's a net flux of 350 Newton centimeters squared per coulomb. Okay. So question in the chat asks, why was x equal to 0 for the first side? And that has to do with how the box is actually sitting. So this is awkward, visualizing 3D things in 2 dimensions, but here we are. So this purple box is sitting so that one side it's like sitting in a corner. One side is tucked along the z-axis, so that would be like the corner of a wall, if you think of it like in a room or something. And the x and y axes, so the box is also touching the x and y axes, and so that would be like touching like along the floor, like where the wall meets the floor in the corner of a room. So your box is like shoved in the corner of a room, and the corner itself is the origin. So the first side that we're looking at is sitting on the y-axis. It's the blue. Oh, I guess it's not. Yeah, sorry, it's the blue one. So this blue side is sitting on the y-axis, and so it has an x value of 0 there. So this would be this surface, or this side of the cube would be like in the ZY plane. You could think about it that way if it helps. And so the x value for this surface is equal to 0, the way it's sitting there. And so since the box is 1 centimeter long, it has an x value of 1 for like the opposite side of the box. And so this would be like the side that isn't along the wall, thinking of it like putting a box in the corner of a room. Does that clear that up? Explain what I mean by the dot product. That's not a silly question at all. It's one of those things that you come to physics and they're like, okay, so you just do the dot product, but like you haven't technically actually learned the dot product yet. That's not a silly question at all. So when you multiply vectors, there's a couple different ways to multiply vectors, but one of them is the dot product. And that's the way that the flux is defined. It's the dot product of one vector, the electric field, and a second vector, the area. And so there's actually, like in general, not just specific to this question, but entirely in general, there's a couple different ways of calculating a dot product. So if you have, or you know what, I'm going to make it completely in general to give you just kind of like a general case, and that applies to Gauss's law, calculations with flux, also things like calculating work, also uses dot products, things like that. So if you have one vector A, and we'll say it has an x component in the I hat direction, and I don't know why I did a B, and a y component in the j hat direction, and you have a second vector B, which we'll say has an x component in the I hat direction and same in the y. Or, you know, these could have like an I hat, j hat, and k hat components. I'm just doing 2 to keep it kind of simple. A dot product, so when you add and subtract vectors, that's pretty straightforward. You would just add your 2 I hat components, add your 2 j hat components, and there you go. You'd end up with a vector, and that's that. But when you multiply them, it's more complicated than that. So if you multiply them, call it a dot product, meaning that you're multiplying vectors of A dot B. And there's 2 ways to do this. For one, you can multiply the individual components and add them all up. So you would just take the magnitude of the x component of each of them, multiply your 2 x components together, and add that to the multiplication of the y components or the j hat components. And this will end up giving you a number. So when you do a dot product of vectors, it's a type of, like a way of multiplying vectors, which is literally just defined by this formula that I gave you here. And it gives you a number. Another way of calculating a dot product, it's equivalent, but it is a bit of a different formula, is you can calculate, like you can multiply the magnitude of one vector times the magnitude of the second vector times cosine of the angle between them. And so the angle between them would be like if this is your vector A and this is your vector B with the tails together, this would be the angle between them. And so in the examples that we were doing, the area vector, which is perpendicular to the area itself, the area vector is in the same direction as the electric field. So back to the diagram here, the side was facing the x direction and the electric field was also in the x direction. And so since they were in the same direction, we said, well, the angle between them is 0. So I used this second definition of the dot product, the A magnitude of one vector times magnitude of the second vector times cosine of the angle. And using this definition, because the angle was 0, the cosine of 0 is 1. And so the dot product of the electric field in the area ended up just being multiplying the magnitudes of the two of them. In the chat, someone said the dot product returns a scalar number versus a vector. Yes, absolutely. And when you get into cross products, which I guess you would have seen a little bit of last term, cross products is just the other way of multiplying a vector, and it gives you a vector as an answer. Okay. Someone asked, okay, I'm so glad that helped. This stuff can be so confusing. If the box was sitting further along the x-axis, so not right in the corner, okay, then the flux would be larger in and larger out, but the net flux would be the same if the box is the same size. Yes, that's absolutely right, because the net flux ends up depending on like the difference in x values, not the x values themselves. So yes, if this box is at a different value of x, as long as it was the same width, it could actually have a different, maybe it wasn't a cubed box, maybe the y component was bigger or the z component was bigger. But as long as it was the same width along the x-axis, then since that width would be the same, or the difference in x values would be the same, then yes, it would be the same net flux. Okay, so we are over time, so I'm going to stop that there. Never mind, there's one more question. How do you know which flux is in and which flux is out? Okay. So the electric field was given in the I hat direction. And so when it defines it down in the question here, it just has 350x plus 150 I hat. So for positive values of x, it's going to be pointing in the positive I hat direction. So go back to my diagram here. I wish I had known I was going to use this diagram so much. I would have made it look nicer. These field lines that I drew in this yellowish color, they're pointing in the positive I hat direction, or in the positive x direction. So that means that you'd have one line go something like this. That's awful, but it gets the idea across. This field line, since it's pointing towards the right, it would go through the blue side first. So that would be the in, like that would be going into the box, and then it would come out the green side and be coming out of the box on that side. So that tells you which is like the influx and outflux. Will the electric field lines always be going in that direction? Not necessarily, actually. So looking at how they've defined the electric field here, imagine if x was equal to -1. For example, if x was equal to -1, then you would have a negative number in front of the I hat. So the electric field would be pointing to the left, or pointing towards the negative x values. That's a really good question, by the way. I'm really glad you brought that up. Okay, fantastic. Well, I will stop sharing my screen and we'll end the recording here.